Okay, I think it's time to start the talk. Good morning, everyone. My name is Bowen Drew, and I will be presenting our work on optimizing symbolic computation systems using a classic but powerful technique called hash counting. In this talk, we will look at its implementation in the Julia symbolics ecosystem and demonstrate its significant impact on performance and memory efficiency. At the heart of our work is a fundamental bottleneck in symbolic systems called expression swell. As we manipulate complex mathematical expressions, we inadvertently create thousands or even millions of identical subterms. For this mathematical expression, we this piece of code, and its corresponding data structure is shown on the right. As we can see, there are some duplicate subtrees. For example, the term a plus b, c minus d, etc. So such redundancy leads to a cascade of performance issues, from excessive memory consumption to slower computations, because the system treats each duplicate as a unique object. And our solution for tackling this problem is hash counting. The idea is simple but profound. We never store the same thing twice. By using a global lookup table, we canonicalize every expression instead of a spreading tree with many duplicate branches. So we get a compact graph. Then with hash counting, the tree shown before was transitioned to the compact directed acyclic graph shown on the right in this slide. As you can see, the duplicate trees, such as a plus b, are removed. So this method not only saves memory, but also, very importantly, allows us to check if two complex expressions are identical by using a single lightweight pointer comparison. This takes only complexity O1 time. And our approach is as follows. We implemented this directly within the Julia symbolics ecosystem. A key part of our design was to make it seamless. We modified the core constructors, so any existing code that builds a symbolic expression automatically benefits from hash counting. We use the weak reference dictionary to work with Julia's garbage collector, and also we update downstream algorithms such that it can be aware of the structure directed acyclic graph, and turning such that the adaptive algorithms can leverage the new structure. To test our work, we chose two challenging benchmarks. The first one is a biology model called the BCR system. It is massive and highly repetitive. And for this problem, we expect big wins here. As for the second one is a physics model called XSteam. It is less obviously redundant about unknown variables. This allows us to see how hash counting performs across different problem domains. In our benchmark, we measure performance across the entire symbolic numerical workflow. including the time and memory used for computing the symbolic Jacobian, and also the time for code generation, function completion, and also the numerical function evaluation. For the PCR model, as we expected, the results are fantastic. We see more than 3-fold speed up in the symbolic computation phase, and we cut memory usage in half. By the way, in this diagram, the yellow lines correspond to the result with hash consing, and the blue line is the one without hash consing. And for downstream, the completion and execution were also twice as fast. This confirms that for problems with high redundancy, hash consing is a clear and decisive winner. The XSteam results are a bit more interesting. Initially, hash consing added a small amount of overhead. The yellow line here is the one with hash consing, and we can see the little amount of overhead. And the compiler was able to leverage its shared structure to produce incredibly optimized code. Code generation was 5 times faster, showing this plot. And completion was 10 times faster. The final numerical evaluation is up to 100 times faster. So this shows the true power of hash consing. So it is not just in the symbolic construction, but also for enabling powerful optimizations later on in the symbolic numerical workflow. So after all, what does this mean? First, hash consing works, but its benefits are context dependent. Second, and also most importantly, we must look at the entire workflow. The massive downstream speedups demonstrate that hash consing is a powerful enabling technique for symbolic numerical computation. It proves that this classic software engineering technique is more relevant than ever before as we tackle larger and more complex computational problems. As for future works, we think the most exciting next step could be integrating hash consing with eGraphs to unify expressions that are not only structurally equivalent, but also logically equivalent. For example, 2 times x is the same as x plus x. So we can also make them the same object in memory for some purpose. Furthermore, we also explore ways to share our optimized structures in parallel and persistent environments. This is crucial for modern AI and HPC workflows. So in conclusion, we have shown that integrating hash consing into Julia Symbolics is a real game changer, and it transparently reduces memory and also accelerates every stage of every pipeline of the symbolic numerical computation, from symbolic manipulation to the final numerical evaluation. So this work, I think, shows hash consing is an essential technique for building the next generation scalable, also efficient symbolic tools. Okay, thank you for your attention, and I'd be happy to answer any questions. That
Could you go back to this slide of like the comparison to a tree and the graph?
okay?
For extending the expression.
Do you mean this one?
Yes.
Okay.
I'm sorry. I'm just trying to understand it. And
yeah, you might know on what exactly what the graph is display and how correlates down to the weight.
Okay. For this mathematical expression, there are duplicate terms. As shown in this tree, for example, for this term, it is a plus b, and there's another a plus b here. So this is redundant. So hash constant removes this redundancy by reusing existing mathematical expressions. So in the updated graphs, the term a plus b is reused here.
I have a question about doing this at the semantic level. What sort of challenges do you expect to see for doing hash consing based on logical equality instead of just structural equality?
Okay. Okay, you're asking what the challenges are for integrating it with logical equivalence. So the main use of Julia Symbolics is to manipulate mathematical expressions and also generate efficient numerical code. So we would like to manipulate mathematical expressions that are most efficient and fast for evaluation in the numerical function stage. Does this answer your question?
Yeah.
Okay, thank you.
how would you, for example, show that like x plus 2y is the same as like 2y plus x for something like this? Do you have any ideas?
Sorry, could you say again your question?
Okay. How would you show, for example, like x plus 2y is the same as 2y plus x, because they're structurally different, but they're logically equivalent?
Yeah, so one of the things that is in the design of Symbolics that I don't think was necessarily shown as much here is that Symbolics uses a non-tree format. So there's a tree format for general terms, but there's also different formats that are for other formulations, right? So for example, when you're adding two objects, it's not actually going to use a tree formulation. It's going to use a set with hashes, right? And the reason for that is because if you use a set, right, then you don't necessarily have so if you say you have a tree, right, then you say, okay, I have a node and I have and then I have the part of tree 1, I have part tree 2, right? If you say that you have a set, you don't have an ordering to this array, right? You just have hashes to it. And the reason for this being unordered is because that's effectively encoding the commutivity inside of this operation, right? And but based off of the hash, it will then always order in the same direction, right? So you then have a natural, if you always put things into this form and it's always hashy, if the hashes are correct, are the same, then therefore it must be the same order. So it's naturally going to encode that by things that are two things that are by commutative operations that are the same, it'll automatically make those be equivalent. Same with associative operations as well. And so there's this kind of AC equality that's able to do for things that are like polynomials, right? So things that are adding, so things that are power operations. So there's a few things that have been specifically optimized in that form, and you'll see this in practice because if you do something like x plus y, you'll see that it automatically will give you y plus 2x, and you might say, oh, like, why are you flipping this around or something? It's like, oh, this is the print ordering does not actually exist inside of the symbolic operation. It's storing it just as something that does not have an ordering, and so it won't even remember what your original ordering was because it's just saying there is an object here and it's exactly equivalent to this, so I don't need to store any information about that. And that ends up being a pretty major performance optimization in it.
Thank you.
Are there other well-known symbolic systems that are using consing? Like, when I think of symbolic systems, I don't know why I always think of Mathematica as sort of like the big famous symbolic system. Do you know whether that uses this technology?
Professor, do you mean other symbolic systems that are?
I mean, not the one in Julia, but other systems that are out there in the universe.
I think the famous commercial ones are like Wolfram and Maple, and the open source widely used one is SymPy, implemented in Python, and maybe such.
So what's the answer? Do you know if there is not?
Sorry, do you mean other symbolic systems that also use the technique of hash consing?
Yeah.
To my knowledge, there are comments, let's say some commercial ones, for example, Maple, that employs this technique, but there's no published results or any source code. And other open source symbolic systems have not yet fully deployed the mathematical canonicalization. So our Julia symbolic is the first one that publish the quantified results of showing the benefits of hash consing for symbolic systems.
So this is a bit of a technical question that I'm asking as a user, and if you don't know the answer, I wouldn't be surprised. If I'm running a threaded program with like 20 threads or something, are there actually 20 currently? I'm asking about the current software. Like, are there actually 20 copies of this implicit hash table that kind of exists somewhere in the ether? And yeah, should I be worried in multi-threaded programs that, for instance, like equality comparisons might fail for some reason, or should I be concerned at all or careful in that situation, which is something that I am doing?
Yeah. So with the question about multi-threading, right? So multi-threading is both easy and hard because it's multi-threading, you have shared memory, right? So it actually is sharing the same object, right? Now the thing that you have to be aware of though is, if I make a modification to the object, so if I say modify the metadata, are all the threads aware that this metadata has been modified, right? This is something where actually when we first rolled out the hash consing system, we were like, oh yeah, we're so good, we're so fast and everything. And the first things that were found were multi-threading bugs, right? We worked through them. I think Ayush actually were one that worked through a lot of these with Oscar. So at this point, I think that we have the right locking and everything's in place, so that way it is multi-threading safe. But yeah, it is definitely a question that you have to ask about this. We've done some pretty extensive testing and we've done some pretty extensive analysis. We believe it's multi-threading safe, but because this was a piece that took a bit and it was some pretty hard work. There might be something here or there that we haven't caught, but at least we are pretty rigorously checking it at this point. It's a hard problem, but I believe we got it.
So for how long have this hash consing been used in Symbolics utils and modeling toolkit? Because I'm thinking about whether I have seen the performance shift or whether I've not seen it when I've been using the packages.
We released the changes of hash consing roughly in April this year, as I remember. Yeah.
There wasn't any song spoken for a few
Also, because of the changes of hash consing in SymbolicUtils, previously in modeling toolkits, the option of common subexpression elimination was turned off, but now it's turned on automatically, turned on by default.
Just out of curiosity, what kind of hash function and collision resolution do you use for the expressions that you have? Is it some custom hash function that you guys wrote, or is it like a generic one?
Okay, regarding hash function, the hash constant technique is independent from specific hash function implementation, as long as the hash function adheres to good hashing principles, such as uniform distribution. So we did not modify the hash function in this work.
We have custom hash on JuliaCon, and then there's a WPDs hash on the character use a slightly different hash function than what users think of when they hash some models. So there wasn't something that we have like now.
Any more questions? Okay, thank you.
Okay. Finally, I want to thank my collaborator Ayush and also my colleague Songchen, and also the undergrad student Blanca, and also my advisors Professor Alan Adam and Dr. Chris Rucker for their support. Thank you.